In section 5.5, we look at additional identities as well as how to apply the existing identities to a couple of additional examples. In the first example, we are asked to evaluate the sign of the quantity arcsine of 3/5 plus arctangent of 2 without using a calculator or any tables. So first, I just want to remind you that arcsine and arctangent are the same as inverse sine and inverse tangent. So how do we take the sign of the sum of these two things? Well, the important thing to remember here is anytime you have an inverse trigonometric function, you need to remember that these are nothing more than angles. So let's give those angles a new name. We'll let A represent the angle given by inverse sine of 3/5, and we'll let B represent the angle given by the inverse tangent of 2. Now what we can do is we can rewrite our problem as the sine of A plus B, right? Because A is representing inverse sine and B is representing inverse tangent. As soon as we write it like this, we know that we can use the sum identity. We can write this as sine of A cosine of B plus the sine of B cosine of A. And now to get the answer for this, all we need to do is figure out these four trigonometric values. So how do we do that? Well, remember that you can draw pictures of these angles. So the angle A is the angle whose sine is 3/5. Now, because of the definitions of the inverse trig functions, we know that angle A must exist in the first quadrant, and sine of that angle is opposite over hypotenuse. And this allows us to find the missing side here, which we know is 4, because this is a 3, 4, 5 right triangle. And once we have completed this picture, we can now say that cosine of A is 4/5, and along with that, sine of A is 3/5. And now you see we have the value here and also the value here. Then we just need to do the same thing for the angle B. B is also an angle in the first quadrant. B is given by the inverse tangent of 2, which means that tangent of B is equal to 2. And tangent, we know, is opposite over adjacent. And then we can find the hypotenuse of this triangle by using the Pythagorean theorem. When you do that, the hypotenuse will be the square root of 5. So remember that 1 squared plus 2 squared must be equal to the hypotenuse squared, and this is 1 plus 4 equals the hypotenuse squared, and that says the hypotenuse squared is 5, and of course that means the hypotenuse is the square root of 5. Once we solve for that hypotenuse, we can now give the values for cosine of B and sine of B. Cosine of B is the adjacent side over the hypotenuse, and sine of B is the opposite side over the hypotenuse. And now we just take these four values and substitute them into the expression. So here we have the sine of A, which is 3/5. Cosine of B, which is 1 over radical 5. Sine of B, which is 2 over radical 5. And lastly, cosine of A, which is 4/5. If we multiply these fractions straight across, we get 3 times 1 is 3 over 5 radical 5, plus 2 times 4 is 8 over 5 radical 5, and this is 11 over 5 radical 5. And this is our answer. And of course, you can decide to multiply the top and bottom of this fraction by radical 5 if you want. And this would give you the answer 11 radical 5 over 5 times radical 25, which is 11 radical 5 over 25. And this is because the square root of 25 is 5, multiplied by 5 is 25. And so this is an alternative answer, which is equivalent. But again, the whole point of this problem is to not be overwhelmed when you see this expression, because it looks very complicated. But if you remember the basics, remember that an inverse trig function is an angle, and then give that angle a new name, a simpler name. Then it produces something that you should recognize. In the next example, we want to write sine of 2 inverse tangent of x as an equivalent expression involving only x, and we will assume that x is positive. Once again, we have an inverse trigonometric function here, and we're going to remember that this is nothing more than an angle. And so I'm going to give that angle a new name. I will let A represent the inverse tangent of x. When I do that, this expression now becomes the sine of 2 times A. And now you should recognize that you can use a double angle formula to rewrite this as 2 times the sine of A times the cosine of A. And so to complete this problem, we just need to know what is the sine of A and what is the cosine of A. And so for that, we go to our equation over here. We let A be the inverse tangent of x, and we know that x is positive. That means that angle A is in the first quadrant, and the tangent of angle A is x over 1, right? So remember that when you say A equals inverse tangent of x, you are saying that tangent of A is equal to x, and x is x over 1. And so tangent is opposite over adjacent, and that's what we have here, opposite over adjacent. Now I can solve for this missing side. I will call this missing side r, and we can use the Pythagorean theorem to say r squared equals 1 squared plus x squared. And then if we just take the square root of both sides, we get r is equal to the square root of 1 plus x squared. And the reason we find that missing side of the triangle is because if we want to find the sine of A, we know that sine is opposite over hypotenuse. So we need that side to figure out the sine of A. So we now know that sine of A is x over the square root of 1 plus x squared. And the cosine of A is adjacent over hypotenuse. And that is going to be 1 over the square root of 1 plus x squared. And so now we can take these values and substitute them in for sine of A and cosine of A here. And don't forget you have a 2 there. And so this becomes 2 times sine of A, which is this expression, times the cosine of A, which is this expression. And now if we just multiply these together, multiplying straight across here, we have 2 times x times 1, which of course is 2x. And in the denominator, we have the square root of 1 plus x squared multiplied by the square root of 1 plus x squared, and that is simply 1 plus x squared. And so we've found an expression for this involving only x. So notice that we do not have any trig functions in our answer. Now we're going to focus on some additional identities. Now, as you can see, these identities are really complicated, and in my classes, I never expect students to memorize these identities. This first set of identities here is called the product to sum identities. And you can see what it does is it takes a product, such as sine of A times sine of B, and it converts it into a sum. And when we say sum, we mean either addition or subtraction. So I can have cosine of an angle times cosine of an angle, and that will convert to this. And I can have sine of an angle multiplied by cosine of an angle, and that will convert to this. These formulas are not used very often, but when you need them, they are extremely helpful. In our first example, we are asked to verify the first formula, so that would be this formula here, for the value of A equals 90 and B equals 30. So if A equals 90 and B equals 30, then we will have the sine of 90, and that's 90 degrees, times the sine of 30, also degrees, should be equal to 1/2 times cosine of 90 degrees minus 30 degrees minus cosine of 90 degrees plus 30 degrees. And I'm checking to see if this is true, so I'm putting a question mark here for now. And I went ahead and put the degree symbols here, which should always be there, of course. Now I'm just going to evaluate the left-hand side and the right-hand side independently from each other and show that we get the same answer. So on the right-hand side, we have the sine of 90 degrees, which we know is 1, multiplied by the sine of 30 degrees, which we know is 1/2. And 1 times 1/2 is 1/2. So the left-hand side is very easy to evaluate. On the right-hand side, we have 1/2 multiplied by the cosine of 90 minus 30. 90 minus 30 is 60, and then minus the cosine of 90 plus 30, which is 120. Now, the cosine of 60 degrees, we should all know, is 1/2, but the cosine of 120 degrees, we may not have memorized. So how can we figure that out? Well, if you remember, there's a few ways we can do this. One way to do it is to simply draw an angle that is 120 degrees, so it'll look something like this, and then to make a reference triangle, and then we know that this angle here is 60 degrees, and from there we can label the sides of this 30, 60, 90 triangle. So since this is 30 degrees, I can label this side as 1, but of course it's negative because we're in the second quadrant. This side would be radical 3, and this side would be 2. And the cosine of this angle now is the adjacent side divided by the hypotenuse. And so the cosine of 120 is negative 1/2. All right, now this is not the only way to figure out the cosine of 120, but it is one way to do it. So now coming back over here, we know that the cosine of 120 is negative 1/2. And now we'll just complete this problem. We have 1/2 multiplied by 1/2 plus 1/2. 1/2 plus 1/2 is 1, and so we have 1/2 times 1, and 1/2 times 1 is 1/2. And so as you can see, the left-hand side and the right-hand side equal the same thing when you plug in numerical values for A and B. Therefore, we have verified that this formula works at least for those values of A and B. In the next example, we are asked to write this expression as a sum or a difference. We have 10 times the cosine of 5x times the sine of 3x. So first of all, I need to identify the formula that we're going to use, and I've already brought that in here. Now, why is this the formula? Well, because we have cosine of one angle multiplied by sine of a different angle. And so that's what you see we have here. Sine of an angle multiplied by cosine of a different angle. So the expression we have, 10 times the cosine of 5x times the sine of 3x, let's first understand that this is the same as 10 times the sine of 3x times the cosine of 5x. And so now this portion of what we're looking at can be rewritten using this part of the formula. To do this, we are going to use a equals 3x and b equals 5x. So this becomes 10 multiplied by, and now we're going to apply this formula, which starts with 1/2 multiplied by the quantity, sine of a plus b, which is 3x plus 5x, plus sine of a minus b, which is 3x minus 5x. And now we just need to simplify. Well, 10 times 1/2 is 5. And inside the brackets here, we have sine of 8x plus the sine of negative 2x. Now, we should never have a negative inside of a trig function because we know that all trig functions are either odd or even. So let's remember that sine of negative theta is the same as negative sine of theta. And this is because sine is an odd function. So what that means down here is that I have 5 times sine of 8x, and then this expression here becomes negative sine of 2x. And finally, if I distribute the 5, we have 5 times the sine of 8x minus 5 times the sine of 2x. And there really is no need to keep the parentheses around the 8x and the 2x. If you do, it's fine, but you can also remove them. And so I have rewritten the original problem as a sum of two trig functions. Next, let's take a look at another set of formulas called the sum to product formulas. And these formulas are even more complicated than the others. So in my classes, again, I never require my students to memorize these, but they do come in handy from time to time, and so it is good to at least know how to use them. So in our example here, we want to verify the first formula, so this formula here, for the given values of A and B. So A is 30 degrees and B is 150 degrees. So I'm just going to plug these values of A and B into both sides of the equation to show that they are equal. And so if we do that on the left-hand side, we get the sine of 30 degrees plus the sine of 150 degrees, and this should be equal to 2 times the sine of 30 degrees plus 150 degrees divided by 2 times the cosine of 30 degrees minus 150 degrees divided by 2. And so now we just need to simplify both sides of the equation and show that they are equal. On the left-hand side, we have the sine of 30 degrees, which is 1/2, and the sine of 150 degrees, which is also 1/2. And 1/2 plus 1/2 is 1. And so that is relatively straightforward. Now, I won't get into why the sine of 150 is 1/2, as we've already discussed that in previous videos. On the right-hand side, let's simplify. We have 2 times the sine of 30 plus 150 is 180 divided by 2. And then the cosine of 30 minus 150, which is negative 120 divided by 2. Simplifying further, 180 divided by 2 is 90 degrees. And negative 120 divided by 2 is negative 60 degrees. And we know that cosine is an even function. That is to say, cosine of negative theta is the same as cosine of theta. So this is 2 sine of 90 degrees, and then cosine of negative 60 is the same as cosine of 60. And now we can fill in these values. We have 2 times sine of 90 degrees is 1, cosine of 60 degrees is 1/2. And when you multiply those together, you get 1. And so notice that they are the same on both sides. For our last example, we want to verify the following identity. And verify means to prove. So to prove this, I'm going to start with the left-hand side and show that it is equal to the right-hand side. So on the left-hand side, we have the following. And to simplify this, we can use some sum to product formulas, and I'll bring those in now. And now to prove this, what I'm going to do in the numerator of the fraction is I'm going to be applying this formula, where a is equal to 3x and b is equal to x. And in the denominator of the fraction, I'll be applying this formula, where again, a is 3x and b is x. And I hope you can see the correlation there between these formulas. So what we get then, in the numerator, we have the cosine of 3x minus the sine of x, and that's going to equal this expression, which is negative 2 sine of 3x plus x divided by 2 times sine of 3x minus x divided by 2. And in the denominator, we will use this formula, which becomes 2 times the sine of 3x plus x divided by 2 times the cosine of 3x minus x divided by 2. And now we just need to simplify. And so what we have in the numerator is negative 2 sine of 4x divided by 2, which is 2x, times the sine of 2x divided by 2, which is x. And in the denominator, we have 2 times the sine of, once again, 2x here. And in the second one, this is cosine of x. And now you can see that the sine of 2x cancels, the 2 also cancels, and what you have left is negative sine over cosine, and that is negative tangent of x. And so we have verified that this expression here is equal to negative tangent of x. And I will tell you this, if you don't know these sum to product formulas, you can prove this identity using other methods, but it takes about 15 to 20 minutes to do so. So these formulas save us a lot of work here.